Now see a torque on current loop. So see, suppose I have taken, there is a rectangular loop like this. This is your P, Q, R and S. Current is flowing in this way, that is in anti-clockwise direction, and this plane of the loop is making angle theta with the magnetic field. So angle theta is with the plane of the loop. So here magnetic field is like this, and here magnetic field is like this. This is theta. So now see here, this loop is placed in the magnetic field, where angle between the plane of the loop and the magnetic field is theta. Now we have to calculate force acting on each sides. So see here, we can assume here PQ is equal to, here SR is equal to, suppose A, that is the length of this, PS is equal to QR is equal to B. These are the lengths of the sides of the rectangular loop. So first we see the force acting on the side PS. So we can calculate force acting on the side PS. We can write F1 is equal to, now F1 is equal to B I L is the length of the PS that I have already taken, that is B. So in place of L I can write here B and sine 180 minus theta. So sine 180 minus theta, this is the actually angle between here the length, that is the current element, and B. So we can write F1 is equal to BIB sine theta. Its direction will be here this side, that is here F1 we can take. Similarly F2 we can take over here. So force acting on QR we can write, that is F2 is equal to BIB sine theta, because here with the current element and B's angle is theta. These two forces are acting along the same line, having equal magnitude and opposite in direction. So they will cancel out each other and their resultant force is 0. And also they do not produce any torque because they are acting along the same line. Now we can take force on PQ and RS. So force on PQ, we can use here the Fleming's left hand rule to find out the direction of the magnetic force. We will be getting magnetic force to this side, that is F3, and magnetic force to this side, that is F4. An angle between here, this is a current element and magnetic field, is 90 degree. So we can write here F3 is equal to BI, and this I have taken here the PQ and SR is equal to A. So BIA sine theta, that is the theta is 90, that is sine 90 is 1. Similarly we can write F4 is equal to BIA. But see here, these two forces are acting here. F3 is acting here outward to the plane of the paper and F4 is acting inward to the plane of the paper. And these two forces are also equal in magnitude but opposite in direction. They are forming a couple, but these two forces are acting along the same line, along the different line of action. So they will be producing torque on the coil. So now we have to calculate the torque acting on the coil. So we know it. Torque is equal to magnitude of the either force into the perpendicular distance between these two forces. So we can write here, we can get the perpendicular distance between these two forces. So let us draw another diagram to calculate here, or to show the perpendicular distances between the two forces. So suppose I have taken this side is here PS, current was here I, and I can take F4 to this side, F3 is to this side, and now this angle is theta, and here we can take this was B. So this is a B cos theta. So we can write the magnitude of the forces are known to us here. We have to calculate torque. So we can write torque is equal to magnitude of the either force, that is BIA, into perpendicular distance between these two forces, that is B cos theta. A into B is the area of the coil. So, we can write torque is equal to BIA cos theta. Now, suppose if the coil has got n number of turns, n is the number of turns, then we can write torque is equal to BNIA cos theta. And NIA can be written the magnetic dipole moment. So, we can write here torque is equal to MB cos theta. But see here, this is the theta between the angle between the plane of the coil and magnetic field. So, this theta is this angle actually. So, now we have to write in vector form. So, we have to take the angle between the magnetic dipole moment and magnetic field. So, magnetic dipole moment is here in this case when the current is going anti-clockwise, that is the outward to the plane of the paper, that is called area vector of the coil. Suppose the area vector of the coil is coming to this side or the magnetic dipole moment, and this angle is, suppose I have taken alpha. So, now we can write theta plus alpha is equal to 90 degree, where the alpha is the angle between magnetic dipole moment and magnetic field. So, theta plus alpha is equal to 90. So, theta is equal to 90 minus alpha. So, torque is equal to MB cos 90 minus alpha, and that can be written torque is equal to MB sin alpha. And we can also write torque is equal to vector M cross vector B. It means torque is acting perpendicular to the plane of the perpendicular to the magnetic dipole moment as well as magnetic field. And see here, whenever the alpha is 90 degree and theta is 0, in that case the torque is maximum. And see here, in this case the magnetic field is parallel to the plane of the coil, and when the magnetic field is parallel to the plane of the coil, the angle between area vector, that is magnetic dipole moment, and magnetic field is 90 degree, and maximum torque acts. In case this type of the magnetic field is there always maintained, that is known as radial magnetic field, which always gives maximum torque and constant magnitude of the torque. So, this is about the torque acting on the rectangular coil, and now we will be using this principle to make the moving coil galvanometer.